The year is 1938. The world stands on the edge of war, but in Berlin, scientists are chasing a different kind of power. In their labs, they probe the atom, once thought indivisible, now revealed to have a nucleus brimming with energy. A handful of brilliant minds wonder, can this energy be unlocked? They bombard uranium with neutrons, hoping to create heavier elements, but the universe has other plans. They share findings across borders, building a worldwide conversation about the secrets of matter. In that fateful year, a Berlin team conducts an experiment that will become legendary for one reason, but hides another secret for nearly a century. The story of that message and its rediscovery today could change how we power our world and reach for the stars. The dawn of the nuclear age was not just about splitting atoms, but about opening doors to the unknown. Otto Hahn and Fritz Strassmann are remembered for discovering nuclear fission, splitting uranium atoms and unleashing immense energy. Their work changed the world, powering reactors and bombs and capturing global attention. But in their rush to understand uranium, they also experimented with lighter elements like lithium. These quieter experiments were overshadowed by the drama of fission and soon forgotten. The world was captivated by the power of splitting atoms, leaving subtle findings buried in old journals. As war erupted, nuclear physics shifted from discovery to weaponization. The overlooked results with light elements became a historical footnote, a curiosity for science historians. No one realized these dusty pages held a clue to a different kind of nuclear reaction, a reaction that could offer a new path to clean, abundant energy. The story of nuclear science is not just about what we discovered, but what we missed. Sometimes the most important clues are the ones we overlook. Hahn and Strassmann's forgotten experiments would one day resurface, offering hope for a new energy future. The world moved on, but the secret waited. It was a whisper in a storm, ready to be heard by those who would listen. The race to build bombs buried the promise of something greater, but history has a way of circling back to its lost treasures. Fast forward to July 30th, 2025. The world faces a new crisis: energy and climate. Fusion, fusing light atoms like hydrogen, has long been the dream, but it's proven nearly impossible on Earth. A team at the University of Wisconsin digging through old literature rediscovers Hahn and Strassmann's forgotten lithium experiments. Intrigued, they decide to recreate the 1938 experiment with modern technology. Using a particle accelerator and advanced detectors, they revisit the old reactions with unprecedented precision. Their goal: see what really happens when low-energy neutrons hit light nuclei. Science usually moves forward, but sometimes, progress means looking back. The Wisconsin team suspects the original results were incomplete, limited by the tools of the time. With today's technology, they can analyze every particle and every trace of energy. They're ready to settle the question: did the past hold a secret we missed? Recreating history is rare, but sometimes it's the only way to move forward. The experiment is a bold leap, putting 1938 under a 21st century microscope. They want to know, can a whisper from the past become a roar for the future? The answer could change everything we know about nuclear energy. Sometimes the key to the future is hidden in the shadows of history. The Wisconsin team is about to find out. The Wisconsin experiment delivers a shock-bombarding lithium with low-energy neutrons creates helium, a form of nuclear fusion. This isn't the hot fusion of massive reactors. It happens at much lower energies. Hahn and Strassmann likely saw hints of this in 1938, but their tools couldn't confirm it. Now, with modern detectors, the signs are clear new elements, clean energy, and no long-lived radioactive waste. This isn't the cold fusion of 1989. It's a real, rigorously confirmed nuclear reaction. It requires less extreme conditions than traditional fusion, opening a gentler path to the same goal. For decades, science chased hot fusion, but this discovery reveals a parallel path. Fusion might not require brute force heat and pressure, just clever physics. It's a paradigm shift. The universe has more tricks than we imagined. A breakthrough hiding in plain sight for nearly 90 years. The discovery suggests multiple routes to fusion energy. It's like finding a calm river to the ocean, while others battle a stormy sea. The implications are profound, a new way to achieve clean, abundant energy. Sometimes the biggest discoveries are the ones we almost missed. The past just handed us a new future. This discovery could rewrite our approach to fusion energy. Until now, the focus has been on massive, complex machines like tokamaks, costly, slow, and challenging. The Wisconsin results point to a different kind of fusion device, smaller, simpler, and potentially cheaper. Imagine fusion reactors that fit in a neighborhood, not a stadium. By avoiding extreme temperatures, we could sidestep many engineering hurdles. This could democratize fusion energy, making it accessible worldwide. It doesn't replace hot fusion research, but adds a new, promising path. Like searching for a cure, we now have more than one promising treatment. The next challenge: make this low-energy reaction self-sustaining and efficient. The original experiment used a particle accelerator, a power plant must keep itself going, but now, the challenge seems within reach. We have a new starting point, a new recipe for fusion. The playbook for fusion energy just got a radical update. Science advances by opening new doors, not just following old paths. The future of energy may be closer than we think. What does this mean for us and our planet? The implications are huge. Lithium, the primary fuel, is abundant. The product is harmless helium. No greenhouse gases, no long-lived radioactive waste, just clean energy. Imagine compact power plants providing energy to communities with minimal environmental impact. No meltdown risk, no toxic waste, solving nuclear's biggest public concerns. This technology could power desalination plants, create green hydrogen, and revolutionize transportation. It could even power our journey into space, compact reactors for Mars missions and beyond. The solar system could open up, turning science fiction into reality. Permanent lunar and Martian bases powered by clean fusion become possible. Of course, we're not there yet. This is just the first step. But it's a step filled with hope and possibility. Sometimes the answers to our biggest problems are hidden in the past. Scientific curiosity is humanity's greatest asset. Rediscovering forgotten knowledge can light the way to a brighter future. The journey from past to present could power the world and our dreams. This story shows how science really works. A winding path, not a straight line. A forgotten discovery from 1938, revived in 2025, reminds us that knowledge is never truly lost. The universe hides secrets in plain sight, waiting for the right moment and the right minds. The Wisconsin team stood on the shoulders of giants, building on the work of Hahn, Strassmann, and Meitner. Science is a conversation across generations, a collaboration between past and present. Every scientist adds a piece to the cosmic puzzle. What other secrets lie in old notebooks waiting to be found? This discovery urges us to revisit history with new eyes and open minds. The next leap forward might begin with a step backward. Even our biggest challenges can be solved by unexpected breakthroughs. The universe is full of elegant, surprising solutions, if we keep looking. Curiosity and exploration are our most powerful tools for shaping the future.